Hi everyone, I'm going to handle the paper as digital signal processing. In that we focused on properties of DFT, discrete Fourier transform. So this is the first unit. Now let me see that the review of DFT. In your SS you have studied DTFT and DTFS, discrete time Fourier series and discrete time Fourier transform. For the semester you have focused about DFT, discrete Fourier transform. So in that it is a powerful technique, powerful tool which allows to evaluate the Fourier transform, that is x of e power j omega on a digital computer. So while here, what is the focus? What is the focus is that the DTFT and DFT is that the DFT is focused on the sequence of finite length. So here, since x of e power j omega, it is a continuous and it is a periodic. So what do you mean by periodic? The periodic sample means that it is a finite period. So that the DFT is applied by sampling one period of Fourier transform at a finite number of frequency points. So as we know that, what do you mean by transformation? What is the need of transformation? The transformation is that the time domain into frequency domain. In that, the transformation between the time and frequency domain is performed with the help of Fourier transform. But why do we go for the discrete Fourier transform? It is inconvenient for computation of DSP processor. That's why we go for the DFT, discrete Fourier transform is used here. Now we will take the n samples. Here the value n, capital, the denotation of capital N stands for the number of samples. So the number of consecutive samples of x of n, so it is a discrete, that's why it is x of n, and that n value is varying from 0 to n minus 1. So the total number of sample is n, therefore it is varying from 0 to n minus 1. It is a periodic sample or a periodic sequence. Then the endpoint DFT, discrete Fourier transform of x of, that is x of k, is x of k stands for the discrete Fourier transform, which is equal to the summation of small n varying from 0 to n minus 1 x of n into e power minus j 2 pi n k. So this is by DFT, discrete Fourier transform of the sequence x of n. So similarly, for if you want to find out the IDFT, inverse discrete Fourier transform, how do we get? Here the DFT, you will take the sample, n number of samples, and DFT coefficient of x of k is taken. Here the k value is varying from 0 to n minus 1. For this, the n sample varying from 0 to n minus 1 can be recovered by using endpoint inverse discrete Fourier transform, that is x of n, that is x of n, which is equal to 1 by n summation over k varying from 0 to n minus 1 x of k into w suffix n minus kn. So what is w suffix n? That is called as twiddle factor. So the twiddle factor is w suffix n is known as the twiddle factor, which is going to identify where the values were lying from plus 1 to minus 1 or plus j to minus j. In some instant 1 by root 2 plus or minus 1 by root 2 j. So this is called as the twiddle factor, which is equivalently e power minus j 2 pi by n. So this is the basic concept of DFT and IDFT. Now let me see that one simple problem of DFT and IDFT. In that, the DFT problem is, see the problem, find the sequence, find the discrete Fourier transform of a sequence x of n is equal to 1, 1, 0, 0, and find the IDFT, inverse discrete Fourier transform of y of k, that is y 1, 0, 1, 0. In that, you need to find out the value of x of k, and from that IDFT you need to get the value of y of n. So as we know that, first we will consider how you will count the number of samples, identify the number of samples. Here n is equal to L is equal to 4, because 1, 1, 0, 0, therefore we have 4 number of samples, therefore the n value is equal to 4. So from this I need to get x of k. So from this, as we know that the DFT formula is summation n varying from 0 to n minus 1 x of n into e power minus j 2 pi n k divided by capital N, where k varying from 0 to n minus 1. So from this, the k value also varying from 0 to n minus 1, therefore here the n value is 4, therefore 0, 1, 2, 3, therefore n minus 1, that is 4 minus 1 is equal to 3. Therefore I need to get x of 0, x of 1, x of 2 and x of 3. So from this, first I will take k value is equal, I will consider k value is here for this part k is equal to 1. So therefore the summation n varying from 0 to 3, x of n into e power minus j 2 pi n divided by k, that is k value is equal to that is n value is equal to 4, therefore which is equal to, first thing is n is equal to 0, substitute n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. So for this part, x of 0 into e power 0, what is e power 0? It tends to be 1, therefore x of 0 into 1 plus x of 1 into e power minus j 2 pi n k, n value is 1, therefore by 2, that is k value is 4, therefore that is 2 by 4, that is equal to 2 to cancel, therefore divided by 2. So this is x of 1, similarly x of 2 plus x of 3. For this, what is the given value? X of 0 is equal to 1, x of 1 is equal to 1, x of 2 is equal to 0, x of 3 is equal to 0. Therefore those two parts should be 0. Therefore 1, the x of 0 value is 1, 1 plus, and x of 1 is 1, therefore 1 into the e power minus j pi by 2, that is e power minus I theta is equal to cos I theta minus I sin theta. Therefore here theta value is pi by 2, therefore cos of pi by 2 minus j sin pi by 2. So therefore as we know that cos of pi by 2, cos 90 is 0, therefore sin 90 is 1, therefore minus j into 1, therefore the resultant value is 1 minus j. Similarly, we need to get the value of x of 2 and x of 3. So you need to substitute the subsequent values about this formula. You need to get the value of x of 2 is equal to 0 and x of 3 you need to get the value of 1 plus j. So therefore, what about the DFT sequence for this formula from this problem is x of k is equal to, what is the first value? 2 and 2 comma 1 minus j comma 0 comma and 1 plus j. So this is the DFT sequence of the given problem. And you need to find out one more thing is IDFT, inverse discrete Fourier transform of y of k. You need to get y of n value. So what is the formula for IDFT? 1 by n summation n varying from 0 to n, k varying from 0 to n minus 1 into y of k e power plus j 2 pi n k divided by capital N, where the number of sample is varying from 0 to n minus 1. So from this you need to get here the number of value n varying from 0 to n minus 1. The number of values sample is 4 minus 1 is 3, therefore 0, 1, 2, 3. Therefore you need to get again y of 0, y of 1, y of 2, y of 3, like you need to apply for inverse discrete Fourier transform formula. We will see that the first thing is 1 by 4 into, that is 1 by n. What is 1 by n? N value is 4, 1 by 4, and y of 0 plus y of 1 plus y of 2 plus y of 3. From this, what is the previous given problem is that, see that 1, y of 0 is 1 and y of 2 is 0 and y of 3 is 1 and y of 4 is 0. Therefore, only two parts is essential. What are the two parts? Y of 0, y of 1 and y of 3. Therefore, we will consider here it is 1 plus 0 plus 1 plus 0, therefore 2, 1 by 2 by 4 it is equal to 0.5. Next thing is y of n. Y of 1 is equal to, similarly, you will substitute n value is equal to 1 and k value varying from 0 to 3, therefore y of 0, y of 1, y of 2 and y of 3. So y of 0 into e power 0 is 1, y of 1 into e power j pi by 2 and y of 2 into e power j pi and y of 3 into e power 3 j pi by 2. So from this value, y of 0 value is 1 and y of 2 value is 1. The remaining part is 0. Therefore, 1 plus 0 plus cos of e power j pi. E power j pi stands for cos of I theta is cos theta plus I sin theta. Therefore, theta value is pi. Therefore, cos of pi plus j sin pi. As we know that cos pi and what about j sin pi? Cos pi is equal to 1. Therefore, it is 1. Therefore, the resultant value 1 by 4. 1 into 1 plus 0 minus, so cos pi is equal to minus 1 plus 0. Therefore, the resultant value is which is equal to 0. Similarly, you need to get the value of y of 2 and y of 3. So what about the sequence y of n? By using the inverse discrete Fourier transform, y of n is equal to 0.5, 0, 0.5, 0. So this is the way to find out the value of DFT and IDFT. So you can focus about the practice problem. The problem is determine the 8-point DFT of the sequence x of n is equal to 1, 1, 1, 0, 0. From this, a number of sample is equal to 8. So from this, by applying this formula, you need to get the value of x of k. So that the DFT sequence value is like this. So you need to try it out. So this is your practice problem. Now the focus. The focus is that the properties of DFT. So what is the properties of DFT? You see that the first property is periodicity. Periodicity, it is a finite sequence. DFT is only applicable to the finite sequence. That is it should necessarily satisfy the periodicity with the period, finite period. Therefore, it is a time domain and frequency domain. Our transformation is only conversion from time domain information to the frequency domain. So DFT is fully based on the frequency domain informations. So x of n is equal to x of n plus capital N, and the frequency domain is x of k is equal to x of k plus capital N. So here the n value is to be added, therefore the frequency domain information also to be added. And the linearity, as we know that linearly added two signals, therefore the consequent the coefficient also to be multiplied. A1 x1 of n plus A2 x2 of n. Therefore x1 of n and x2 of n are the two sequences to be linearly added. So by the coefficients A1 and A2, therefore the resultant, the DFT Fourier transform frequency domain information also the coefficients to be multiplied, like A1 x1 of k plus A2 x2 of k. Similarly, the third property is time reversal. What is meant by reversal? The time to be reverted. Here, x of capital N minus n, so it is reversed by capital N. Therefore, the frequency domain also capital X of capital N minus k. And what about another property, circular time shift? So that circular time shift is x of n minus l into power suffix n, which is equal to x of k into, it is circularly time shifted e power minus j 2 pi kt divided by 2 pi kl divided by n. And another property is circular frequency shift, that is x of n into e power plus j 2 pi kn divided by 2 pi ln divided by capital N, that is equal to x of k l minus n. And then another one is circular convolution. The convolution means that two signals to be multiplied. Here the circularly convoluted x, that is x1 of n, so that this n within a circle, that is called circularly convoluted with the sample number of samples n, that is in x2 of n, which is equal to x1 of k into x2 of k. Like that, the circular correlation. So what is correlation? So one signal is the real signal, another one is the conjugate signal. x1 of n circularly correlated with y conjugate of minus n. Therefore, you can get x of k into y conjugate of k. So now the next property is multiplication of two sequences x1 of n and x2 of n. So now what we get, the Fourier transform is in frequency domain 1 by n into x of k into circularly converted with x2 of k. And the last one is the complex conjugate. So complex conjugate stands for x conjugate of n. So x conjugate of n stands for, therefore the frequency domain also capital X conjugate of n minus k. Now the last property is the Parseval's theorem. So Parseval's theorem is two signals to be multiplied with the help of summation of n varying from 0 to n minus 1 x of n into y conjugate of n. So one signal is the real signal, another is the complex conjugated signal. For this case, the frequency domain information is 1 by n summation over k varying from 0 to n minus 1 x of k into y conjugate of k. So these are the list of properties. Have been studied for the DFT. And see one by one by the proof, as we are focused about the periodicity. First thing is, as we know that x of n is an input sample. If you can apply the DFT, you can get x of k. If the sample to be added with capital N, therefore x of n plus n is equal to, which is what is the equivalent, x of n plus n is equal to x of n, that is you need to prove it. And in terms of frequency domain information is x of k plus n, that is equal to x of k. Now let me see the proof. As we know that the DFT of x of n is, that is equal to x of k, which is equal to, what is the formula, k varying from 0 to n minus 1 x of n and e power minus j 2 pi k divided by capital N. For this, here the sample x of k, this k to be added with the number of sample capital N, therefore x of k plus n. Therefore, wherever you have the k, you can add plus n. Therefore, e power minus j 2 pi k. For this 2 pi k plus n, 2 pi k plus n whole divided by n. So for this case, you can multiply inner product e power minus j 2 pi k n divided by capital N, and e power minus j 2 pi n cancel. Therefore, e power minus j 2 pi, what is e power j 2 pi stands for cos of 2 pi minus I sin 2 pi. So for this value 2 pi, any sin of n pi value is 0 and cos of n pi is 1. Therefore, this value, the resultant value is 1. Therefore, this coefficient part to be retained, that is equal to summation n varying from 0 to n minus 1 x of n and e power minus j 2 pi k divided by n, which is equivalent to x of k. Therefore, if you are going to add the number of samples, that is also equivalent to the x of k. Therefore, it satisfies the property of periodicity. The periodicity with the period of n samples, it is not changed for the discrete Fourier transform. And the second property is linear property. As I told earlier, x1 of k and x2 of k are linearly added. Then with the coefficient of a and b, therefore x1 of n and x2 of n, two samples to be added with the coefficient of a and b. Therefore, the resultant DFT sequence also multiplied with the coefficient of a and b, a x1 of k plus b x2 of k. And the third property is shifting property, time shifting property. So here this signal, I will take the sample as a periodic signal. That's why I have mentioned here it is suffix p. Xp of n is equal to summation l minus into plus into x of n minus ln. So n stands for number of samples with the finite period. Now you need to shift the sequence. How can you shift the sequence? Xp of n have been shifted by k samples. So it is a time delayed. Therefore, xp of n minus k, which is equal to, it is equal to it as for in general n minus ln. Here it is n is replaced as n minus k. Therefore here you can replace x of n minus k minus ln. So that is equal to x dash of n is equal to x dash of t, and that is called as shifting the property. If you are going to shifting the property, there is no need to worry about the shifting the property. The same thing to be repeated. X p of n is equal to x p of n minus k. We are going to shifting the property. The formula have not changed, only the shifting the time to be shifted. So this property is called as shifting the property. Another one is the circular shift, that is x conjugate of n is equal to x of n minus k. So here this is called as n minus k comma modulus of n, modulo operation of n. The next one is time reversal sequence. So how can we say that it is a time reversal? As we know that x of n, you can take a DFT and we can get x of k, and this is called the time reversal property. Here x of minus n comma modulus of n, that is equal to x of n minus n. This is DFT. Using a DFT, what we get, capital X into small x into capital X, that is a DFT, and minus n tends to be minus k, and modulus of n as it is, and minus of x of n minus n tends to be capital X of n minus k. Therefore, whatever we have been reverted, here the DFT sequence also reverted. Therefore, this endpoint DFT sequence is a time is reversed. And the next one is the circular time shift. So how can you say that it is a circular time shift? Here see that x of n minus l comma modulus of n, modulo operator of n. So we can apply the DFT property. We can get x of k into the time to be shifted. Here e power plus this operation, modulus operator tends to be e power plus j 2 pi n k by n. So the last one is the circular frequency shift. So what is the circular frequency shift? See that x of n, you can take a DFT x of k. So from this e power x of n is multiplied by e power j 2 pi n k by n. So here the frequency should be shifted, which is equivalently in DFT x of k minus l and modulus of n. So this is called time shift, and this is done to be frequency to be shifted. And another property is complex. So complex conjugate property, as we know that x of n tends to be x of k, and the complex, this symbol conjugate star symbol in prefix we have symbol called as the conjugate. X conjugate of n, we can take a DFT, we can get x conjugate of minus k comma modulus operator of n, that is equivalent to it as a capital X conjugate of n minus k. Therefore, if in reverse operation, I will take I'm going to use the IDFT. So x conjugate of n minus k, x conjugate of k, which is equal to, in general formula, 1 by n summation k varying from 0 to n minus 1, x conjugate of k, that is a small x conjugate of k, e power j 2 pi k n divided by capital N. So that is equivalently, you can take the whole sample to be conjugated. Therefore, the whole sample modulus to be conjugated. Therefore, x conjugate of minus n comma modulus operator n, which is equal to x conjugate of n minus n is equal to by taking a DFT a capital X conjugate of k. Therefore, x conjugation, the conjugation to be applied over here. Therefore, if you are going to shifting the samples, small n tends to be capital N, and if you are conjugated by the sample of n minus k. And the next property is a circular correlation. So what is a correlation? If two signals are access, autocorrelation, cross correlation. So the same sample to be taken care, that is called autocorrelation. If different samples are taken care, that is called cross correlation. So here x of n and y of n, we have two samples in different sequences, x of n and y of n. Therefore R, this R stands for correlation of xy, suffix xy, that is called cross correlation of t. R xy of t, I will take the first one, x of n into x of k and y of n into y of k. By this, I am going to take the IDFT 1 by n R xs of k minus x of k into y conjugate of k. So from this, R x of l is the unnormalized circular correlation sequence. This is called cross correlation. Y, x of n and y of n are the two different sequences. Therefore, R x y of l, which is equal to, for the DFT, summation n vary from 0 to n minus 1, x of n into y conjugate of n minus l into modulus operator of n. One sequence will be real sample, another one is a conjugate. Therefore, it is a time shifted by the value is l, n minus l. And the next property is multiplication of two sequences. So x1 of n and x2 of n. So I will take x1 of n, x1 of k, and x1 of n, x2 of k. So for this, I am going to multiply two sequences by applying the DFT, that is equivalently 1 by n x1 of k into this within n number of samples within a circle is called as the multiplication operator into x2 of k. The last properties of Parseval's theorem. The Parseval's theorem is, so the Parseval theorem is, it is a complex valued sequences like x of n tends to be x of k and y of n tends to be y of k. The one sample is the real sample, another one is the conjugate sample. So a summation n equal 0 to n minus 1 x of n into y conjugate of n, that is equivalently written as 1 by n summation k from 0 to n, that is x of k into y conjugate of k. So from this above equation can reduce as summation, two sequences are multi-equivalent. So summation n vary from 0 to n minus 1. Modulus of x of n square is equal to 1 by n. 1 by n, that is called Parseval theorem. Number of samples 1 by n. Summation n k from 0 to n minus 1. X of k and y of k are equivalent. Therefore, x of k to be squared. So this theorem is said to be a part. This expression relates to the energy on in the finite division of the sequence to the power and the frequency component of x of k. Thanks for listening. Thank you everyone.